not like, and I think older people know this.
Did you grab test, did you?
Me?
Yeah.
I got like 2 of them.
All right. Let's get started, everybody. So welcome. Hope you're all well. Welcome to the revision for our last test. So that means you've learned everything you need. You've learned everything you need for the Year 12 Methods course. So well done. So we just focus on the next week. So we've got 3 revision lessons, including today, leading up to the test next week. So 168 hours time, you'll be sitting down to do your test. All right, so what we've got here, we'll start with the test summary. We'll go through a few of the questions together, and I'll just point out a few things. So the first sheet of paper is the test summary, like we normally do. And then the second sheet of paper is stuff that I've cropped out of the textbook in the past, and that's basically the formulas that we need from chapter 8 and 9. So that's what kind of stuff you should be condensing down to your cheat sheet. All right, so test next Tuesday, lesson 5 and 6. It's a short test, we're 50 minutes, 35 marks, maybe a little bit of adjustment there, 38 marks or something. You get your calculator, bring 1 page of handwritten notes. The content is chapter 8 and chapter 9. Most of chapter 8, apart from the probability density functions, most of chapter 8 is done in year 11. And so that leaves us with chapter 9 and being the sort of where the learning really has occurred. So then we've got our skills checklist. Okay, so have a read through that. Make sure you're comfortable with what like a good revision tool is. What do those words mean? So the first one, calculate the mean, median, mode, and standard deviation of probability density functions. Do I know how to do each of those using a formula and so forth? So have a read. Understand it. If you're not sure, ask me. I can explain what it is, but make sure you know how to do that. Then a list of our revision resources, chapter 8 and 9 review sets. Okay, any questions about the content and so forth before we get into this review together? All right, so I'll speed through this together. Again, all we're doing out with the review is just trying to draw out all of the skills over 3 questions that you can be assessed on. So to begin with, we have a probability density function, which is y equals ax squared, and we're told it's valid from 0 to 1. Part A says find the value of A. So a valid probability density function has 2 properties. The first is that the area under the curve is 1, and the second is that it has to be above the x-axis. You have positive probabilities, you don't have negative probabilities. So what that means is if this is valid over this interval, it means the integral from 0 to 1 of ax squared, the area under this curve, is equal to 1. And so implicit in this is basic integration. You won't be asked complex integrals at all, like the extent of it is integrating a polynomial, but that's sort of an assumed skill for this test from now on. So let's integrate this. I'm going to pull a up front, and the integral of x squared is x to the 3 on 3. And then we'll plug in 1. So a times a third equals 1, and then we'll multiply both sides by 3 to get a is 3. Very good. Okay. Now part B says find the mean, the median, the mode, and the standard deviation. So we can have a look at your formulas there. So that's the second box. All right. So we've got the mode is the value of x, which maximizes the function. So we've got the value of a, so our function is 3x squared, all right? And so we should consider the graph of it. It's going to look like this, the probability density function. Here's event 0, here's event 1, that's the region over which it's valid. And the mode is just the x value that has the highest y value. Well, you can see as you're going further along here, the y value gets higher and higher. So the highest y value is when x is 1. Our mode is 1. We obtain that from the graph, okay, graph the probability density function. It shows you, like, you're more likely to have data on that end than you are on the left-hand side because here's the probability, that's what's on the y-axis. And so the mode, the most common event, occurs when x is 1. Okay, so that's the mode. Next we need the median, and the median is the event here, I'm going to call it m, such that the probability to the left is 0.5 and the probability to the right is 0.5. Right, such that the area under the curve is half. So for the median, I would tend to just use your calculator. You can make a mathematical argument if you want to. In the test, all right, most of them you just have to evaluate yourself using your calculator. You won't be required to show any working because it's sort of a 1 mark question. So we're finding the median, the interval from 0 to m of the probability density function is equal to half. Okay, so it's very similar to equating it to 1. That's the whole area under the curve, but here we have half of the area under the curve. And we type that into equation solver. Now, this might be a good lesson for us to talk about something in equation solver actually. So if we pull it out. So my expectation is you would know how to sort of go through and solve that manually, but I do want to stress something here about equation solver. So if we go to your main menu, go into equation and go into solver, and I'm going to type in this this whole thing here. So we go option, calc, bring up the integral. We've got the integral of 3x squared, and we're doing it from 0 to m. M is an unknown, so we're going to substitute x, and then we're going to equal that to 0.5. Now, before you press evaluate, we restrict the boundaries over which we're required to find a solution. We have the lower boundary and the upper boundary. This is what I want to stress to you. Now, this will have multiple solutions, but we want to localize the solution between 0 and 1. So we're going to restrict the lower boundary to 0 and the upper boundary to 1. Okay, so we're being very deliberate about the solution that it gives us. And now we're ready to solve it. And I get n is 0.793. 0.794. Okay, so I've gone through that. If you're unsure about anything I said there, about setting the boundary or typing it in, you can let me know a bit later, but let's move ahead. So that's the median. Now we need the mode, now we need the mean, sorry. And the mean is just the integral over the boundary. So our integral over the boundary that we've got, that is valid, of x times the f of x function. Okay, that's the probability density function. Here's x. That's going to be the formula for the mean, and we just type that straight into our calculator. So give it a punch. 3x to the 3, it'll simplify too. And I've got 3 on 4, 0.75. Okay, and then the last one is standard deviation. We've got 2 formulas we can use for the standard deviation. So I'll just go with the first one we've got there, which is the square root of the integral from a to b, so from 0 to 1, of x squared times the function with regards to x. Okay, so you're evaluating the integral, then taking away the mean squared, and then square rooting it. Okay, and again, that's just something that we will type into our calculator as well. So what are we going to have? 3x to the 4. Take away 0.75 squared, square root 15 on 20. Okay, so they're sort of 1 mark questions, mostly using your calculator, just plugging in the formulas. Any questions about question 1? Excellent, let's go to question 2. We have the weight of eggs, x, okay? So in brackets x, it's telling you the weight of eggs is the variable x. We randomly select the egg and we consider it as the variable x. It is normally distributed with a mean of 80 grams and a standard deviation of 12 grams. Calculate probability of x being larger than 65 and interpret. Okay, so this is just an NCD calculation. Our lower boundary is 65, our upper boundary is infinity. The standard deviation of x is 12 grams and the mean is 80. So first, 2 steps to this, evaluate it and then interpret. D, so from 65 to infinity, 12 and 80. We've got 0.8943, 0.894. Okay, so what does this mean in the context of it? Well, x is the variable of an egg, right? So you're randomly selecting an egg, and this is a probability calculation. This is the probability that a randomly selected egg is larger than 65 grams, okay? So the probability of a randomly selected egg being larger than 65 grams is 0.894. All right, that's A. B, determine the probability that an egg weighs less than 60 grams. Well, this is the probability of the variable x being less than 60. Now remember for continuous random variables, there's no significant difference between less than and less than or equal to. Both mean the same thing. It's only discrete random variables where we need to consider the distinction between them. So this is just another NCD calculation. Lower boundary this time is minus infinity. I know in terms of the context of the problem, like you don't have the weight of an egg being less than 0, but because of the nature of a normal distribution, it's mathematically correct to put negative infinity as the lower boundary. Okay, so negative infinity to 60, standard deviation is 12, and the mean is 80. I'm evaluating that one. If anyone's got it, you can tell me. There we go. 0.0477. 9. Okay, so 9 rounds. 0478. All right. So again, writing the first four figures, and then rounding the fourth figure gives you 3 significant figures, unless otherwise stated. All right. C. An egg is jumbo if it's in the largest 10% of eggs. Jumbo eggs. What is the smallest weight a jumbo egg can have? Okay, so here's the distribution of eggs, right? It has a mean of 80 grams and a standard deviation of 12 grams. And we're saying the largest 10%, these are those jumbo eggs in here. And we want to know what's this value K, such that it's the smallest jumbo egg. Okay, what's this value K, such as the smallest jumbo egg? So what we have, this is an inverse normal calculation, right? The probability of x being larger than k is 10%. So this is inverse normal. Our tail is pointing to the right, and we've got our areas and standard deviations. Tail right, area 0.1, 10%. Standard deviation 12, mean 8. Thank you, Tyler. Right, 0.1, 12 and 8. 95 grams. So if you have a 95 gram, 95.37, which is 95.4 grams, that's going to be the weight of an egg. That makes it jumbo. Okay, so that's good. Any questions at this stage? All right, keep cruising along. Then we have, there are 12 eggs in a carton. Let the variable S12 be the distribution that arises from the sum of 12 observations. Is S12 normal? Justify your answer. Okay, so 2 things to say here. When we started talking about S and Xn, we said X is normal. If X is normal, then Xn is normal for all n. Okay? In this circumstance, we have eggs are normally distributed, therefore Sn will be normally distributed for all n. So the answer to D, yes, S12 is normal because the variable x is normal. Okay? Now just to stress, when we were looking at this, remember we said If x is not normal, well, the variable Sn will be normal provided n is sufficiently large. The more observations you make, that's the central limit theorem. The more normal the distribution becomes. And we said if it's larger than 30. Not that larger than 30 is the justification. The justification is sufficiently large. Okay? All right. So that's part D. Yeah. So yes, S12 is normal because X is normal. E. What's the probability that a carton of eggs will weigh more than a kilo? Okay. So this is the probability of S12 being more than 1 kilogram, which is 1,000 grams. So occasionally there is the need to convert units, minutes to seconds, grams to kilograms, what we've done the opposite, kilograms to grams. And we're doing that because the weight of eggs is in grams, and so S12 is going to be in grams, and we're saying what's the probability of S12 being larger than 1,000? So another NCD calculation, our lower boundary is 1,000, upper boundary is infinity. The standard deviation of 12 eggs added together. Okay, so I'll just write this out here for you. The mean of S12 is 12 times the mean of X, all right, which is going to be 12 times 80. And the standard deviation of S12 is square root of 12 times the standard deviation of X. So that's going to be the square root of 12 times 12. 12 root 12. That's cool. So then when we're plugging all this in, we'll have 12 root 12 here, and we'll have 12 times 80, what's that? 800, 960. So 1,000 to infinity and beyond. 12 root 12. We've got 0.168. 0.1679, 0.168. All right, one massive egg weighs 120 grams. This is an enormous egg. How many standard deviations is it above the mean? So this is a z-score question. Remember, a z-score is a measure of how far a result lies above or below the mean. That's the formula for the z-score. So you have your result, 120, take the mean result, which is 80, divided by the standard deviation, which is 12. So what have we got? 40 on 12. So we'll just have just over 3.3. So it's 3.3 standard deviations above the mean. Above because it's positive. Remember, negative z-scores mean it's going below the mean. Very good. Okay, on to number 3. All right, and what I've really drawn out this question because I really want to emphasize how we answer confidence interval questions. So we have a sample of 150 people, finds 96 of them have brown hair. Calculate the 96% confidence interval for the true proportion of people with brown hair. So just in our calculators, you can do it manually if you want, but always go straight to your calculator unless it says fill in the boxes here. You'll see that pop up in some of the practice tests. First proportion, so 96. We'll have all kinds of different levels of confidence. And we have 96 people out of 150. We've got 0.5595, 3A. 0.7204, so 0.5. So that will round, which will make that round 0.560, 0.720. Okay, there we go. There's the 96% confidence interval. Okay, part B. Seb claims that at least 80% of people have brown hair. Is his claim correct? Okay, so if we think of this as like a number line, And the true proportion is somewhere between, we're 96% confident, it's somewhere between 0.56 and 0.72. All right, 0.8, 80% lies up here. Okay, so the claim, his claim is not supported by the confidence interval. Is his claim correct? So we're going to say no. His claim lies completely above the confidence interval. Okay, so the justification is his claim is outside the confidence interval. Therefore, the confidence interval that we've produced, it doesn't support this claim. The confidence interval says we're 96% confident it's somewhere in here. His claim is outside of the domain of our confidence interval. Okay, then we have Matthew, who claims that definitely less than 80% of people have brown hair. Is his claim correct? Okay, so there's a couple of things to say here. Firstly, confidence intervals are never definite. Okay, they don't guarantee truth, they only indicate truth. So we will take issue with him saying definitely. Okay, however, the confidence interval does support his claim. That's what we're going to say. So we're going to be a bit nuanced in our answer. We're going to say the confidence interval supports Matthew's claim. All right, the confidence interval supports his claim. However, confidence intervals do not guarantee truth. So we can't say definitely. That's fine. It's a fine way to answer it. Okay. D. Jill claims that most people have brown hair. Is her claim correct? So most people, this is ambiguous, right? Most people would be anything larger than 0.5. All right? Most people, anything larger than 0.5. Our confidence interval indicates it's anywhere between 0.56 and 0.72. So again, we'd say yes, the confidence interval supports. So Jill's claim lies within the confidence interval, or is supported by the confidence interval. Okay. All right, last one. Then we've got a sample of 200 people who don't use water softeners finds that 100 of them have brown hair. Okay, calculate the 96% confidence interval. So we have 100 people out of 200 don't use water softeners. And we have our new confidence interval. I'm going to write it up and then I'll sketch them next to each other. We have is 0.4273 less than P less than 0.5726. P 0.427. Okay, and I'll sketch both of those up here to illustrate. 0.427, 0.573. Okay, so this is good. I'm sketching them both so we can see, what we can see is that they actually overlap. That the lower boundary of this confidence interval exists within the upper boundary of this confidence interval. Okay, so the first part of that is to find the confidence interval. Is there sufficient evidence to claim that those who don't use a water softener are less likely to have brown hair? Okay, so based off the sample, all right, so we've got a sample of people who don't use water softeners, and the true proportion of people who don't use water softeners and have brown hair is somewhere in here. Whereas the true proportion of the general population is somewhere in here. And because there's an overlap, the claim is not supported. The true proportion could be as low as this one, and the true proportion here could be as high as here. So because there's an overlap, the claim is not supported. So in order to answer that in words, now with confidence intervals, okay, there's 2 marks, normally all the time, 2 marks, and it's always answer the claim, then justify, okay? And that's how we've written all of these out. Is the claim correct? Is the claim correct? Does the confidence interval support the claim? So in this circumstance, is there sufficient evidence to claim that those who don't use a water softener? No. The confidence intervals overlap. Now what this means, okay, what it means is that the true proportion, so if it's going to get a little bit convoluted here, but let me just have a write for a minute and then I'll talk. The true Alright, so there, what have I said? I said the true proportion of people who use a water softener and have brown hair could be as high as low, could be as low as 0.56, okay? So here they're using a water softener and they have brown hair, could be as low as 0.56. Whereas the true proportion of those who don't use a water softener and have brown hair could be as high as 0.57, so, sorry, as high as 0.573. So because there's an overlap, all right, there isn't sufficient evidence to claim that there's a discrepancy, okay? It can be justified as a statistical anomaly. All right, so confidence intervals, they're never guaranteed truth. It's always about, does the confidence interval support the claim? Yeah, any questions about our review there? All right, really good. So we've got our revision resources.